This conference will now be recorded.
Hello, my name is Glenn Charest. I'm a mechanical engineer at Facebook.
And I'm Stephen Moore, a project engineer from RITA.
Today, we're going to be giving an update on the OpenRack version 3 frame. We're going to give a brief overview. We're going to talk about frame design and manufacturing. We're going to talk about rack rail designs, conversions of V2 to V3 gear, what's involved in that, OpenRack V3 liquid cooling, and then what's next. This table is a brief comparison of some of the differences between V2 and V3 rack. V3 will have 48-volt support. The power shelves will be able to be moved in any rack slot, unlike V2, where it has to be in specific areas. Toolless rack rails will be an option. Excuse me, not an option, but part of the native design. We will also support RU gear support, and V2 does not support that. The gear quantity supported between them has gone up a bit. So in version 2, it supports 40 OU and no RU. In version 3, it supports 44 OU and 48 RU, so you have a choice of doing them, either one. We're going to provide a modular cabling solution in V3 that's not available in V2, so you can optimize that as you need to. Support for an optional rear cable backplane will be available. In V2, it's not supported. We'll have a movable horizontal frame support, where in V2 it's fixed, and the maximum weight supported in terms of IT gear will go from 1,400 kilograms to 1,600 kilograms. So in this slide on the left is the basic dimensions of the rack, 600 by 1086 by 2289. And on the right is a view of the rear of the rack, and we'll go over some of the basic features. Vertical stripe with the middle of the rack is a 48-volt bus bar. It has the same volume as the 12-volt design in the past, but uses a different connector. We're also going to be having an optional hot plug data bus backplane. It can either be optical or copper. We're also working on, and I'll get into this a little bit later in the presentation, optional liquid cooling solution that will include hot plug dripless interconnects as well as manifolds. And so the picture there with the green stripe, vertical stripe on the left is a representation of a cold manifold, and the red stripe up and down on the right is a representation of a hot manifold. At this point, the plan is to have them split as shown. This just shows, this is a view showing the front of the IT gear and how in OpenRack V3 we'll be supporting either a 48 millimeter pitch to support OpenU or a traditional 44.45 EAI RU IT gear pitch. This is a view of this looking from the front of the rack into the side there. That large black panel with the green cable clips on it, that is now removable. It's not welded in, so you can optimize and design as you need it for your particular solutions. And then in this picture, we're showing the dark strip going left to right is actually a metal bar that is removable, and that's basically the frame support that keeps the opening of the rack within specification. In V2, that's a welded design. You can't move it. You have to put your gear around it. In V3, you can move it up and down. It should still be in a relative middle of the rack, but you have some flexibility to optimize the location of it for your particular configurations.
So now we will cover the topics of the rack design and manufacturing aspects of the ORV3 frame. Here I've listed out the topics that we will cover in this section of the presentation. So first we'll just touch on the optimized weld fixturing, then challenges we have seen around liquid cooling and the manifolds with regards to the frame. Also roll form ready design of the vertical members, then universal vertical members for manufacturability, and we'll cover the shelf variations such as power shelf, OU and RU. Then also the shelf installation of those shelves, also the toolless shelf retention of each shelf, and then finally the catch edge improvement versus ORV2. So here we have an example of the optimized wells fixturing we intend to use for ORV3. This is actually similar to the ORV2 frame today. And as you can see from the image, I have got a blue highlighted tag and a green highlighted tag. The green highlighted tags is what drives the dimension of the vertical members in the frame. And the blue highlighted tags just help guide the part into the correct position for assembly before welding. Some of the benefits gained from designing the rack this way is improved dimensional accuracy, as the dimension is driven from pierce to pierce of both the canopy and base tray to the vertical members. It also reduces the investment and number of jigs and fixtures required to weld these vertical members into the correct position in the frame. It also reduces the amount of time it would take to assemble these parts together for welding, improving manufacturability. Here is an overview of the key challenges we've seen for tolerancing of introduction of the liquid cooling and manifolds. So the image on the right is an aerial view of the ORV3 vertical frame without the canopy. So the blue dimension line you can see at the top of the image, this is an example of what needs to be considered for the liquid cooling and manifolds. So the dimension that needs to be considered is from the front inner vertical member catch edge to the front of the manifold mating face, and then to the rear of the frame where the manifold assembles to. Another key tolerance that we must consider in the frame is the equipment catch edge to the rail stop, which is highlighted in red in the image on the right. So this dimension goes from the front vertical catch edge to the backstop of each IT shelf, and this is where the equipment is stopped. And obviously it needs to be considered in the overall tolerance loop of both the equipment and its mating to the manifold as seen in the other dimension. The final dimension we must consider is the equipment catch edge to the buzz bar mate, which is the green line you can see on the image, which is from the catch edge to the buzz bar. And this is the third and final key dimension, which must be balanced between the other two dimensions I've already mentioned. And so this has been quite challenging during design to ensure that we meet each piece of equipment's requirements. Here is a couple of images of where we intend to mate the cooling manifolds to the frame. So as you can see at the top and the bottom of the frame where we intend to mate, it is both on the canopy, vertical member, and base tray. So the important thing is that these are flat and flush for the mating of the manifold, and obviously this introduces certain challenges such as making sure that these are flush during welding and other issues associated with that. So next we'll touch on the roll form ready design. So for the scope of the ORV3 project, due to the potential for very high volumes of this product, we wanted to design the vertical members to incorporate the possibility of roll forming. It is also part of the scope to ensure that these vertical members were also manufacturable through soft tool processes, not just roll form. And I'll go into a bit more detail in the following slides. So why roll forms? Why roll form? So the key thing is to allow the support of a very high volume for this product, as previously mentioned. This also provides a reduction in piece part cost when you reach this level of volumes. As you can see on the images to the right, there's part 1 and part 2 of the vertical member. And the reason we have this is to allow the part to be both soft tooled and roll formed. If you were to go another route, you would not be able to do both processes. So some of the roll form challenges that we have seen are largely around tolerances of the process. So cumulative piercing tolerances is something we've had a challenge with, which is introduced during roll form, as when the part is pre-pierced and then fed through the rollers, you get cumulative stretching throughout the part. Another challenge we've seen is end cut tolerance on the roll form line, and this has been solved at this point by, if you can see the small hole at the end of the vertical member part there on the image, this is where a pin is fired on the roll form line into the hole to align the position ready for cropping of the end of that part. Another challenge that we've seen is end flare, which is a tolerance issue found with roll forming, and we've had to address this with multiple design actions within the part. And then finally, another challenge we have is the inflexibility of roll form design. So the hard tooling that needs to be put in place for the roll form obviously is not as flexible as normal soft tool processes for manufacture of this part. So there is more of a focus on ensuring this design is right first time and is not as flexible to change post-launch. So here we have a top-down schematic of the universal vertical members that we have introduced to ORV3. As you can see, there is a rear, a middle, and a front vertical member. The rear and the middle vertical members are all identical. We have done this by flipping the vertical members in each direction to allow them to support the functionality in all areas. So for the rear vertical members, they are flipped on their head from left to right, and then the rear to the middle are flipped also on their head over from top back to front. And this allows us to incorporate a unique part for all four vertical members. And then the front vertical members, they are unique themselves, but they do flip from left to right also to help with manufacturability. So the benefits of doing this for the universal vertical members is you increase the large batch quantities at every level of the part and therefore reduce costs during manufacturing. It also simplifies internal logistics of the parts throughout the manufacturing processes, and also reduces potential quality issues seen from having slightly different vertical members that should be in different places of the frame. So here we have an overview of the different shelves that we have currently designed for the ORV3 rack. So we have the power shelf, the OU shelf, and the RU shelf. The OU shelf, as Glenn has mentioned, is the OCP standard height shelf, and the RU is the standard industry 44.45 millimeter height shelf. So the common features between these three shelves is they all have a backstop for the equipment, which is unlike V2, as V2's backstops is within the frame. We have also introduced a toolless retaining feature to each of the shelves to prevent them from sliding out of the frame during shipping and operation. The differences between the three, for the power shelf, they are now shorter than the IT shelves, and this is to allow and create space at the rear of the shelf for the equipment to mate to the buzz bar. The OU shelf, as I've mentioned, is taller than the RU shelf, and this is the only difference between the two shelves, apart from the unique assembly features which prevent them from being assembled into the wrong location throughout the frame, which I will cover in more detail in the next couple of slides. So here is a video of the IT shelf being assembled into the frame. And as you can see, the shelf is dog ear tags, which you can see on the shelf, go into the square holes on the vertical member and slide back for the clip to engage and lock that in place. If you can see some of the squares on the inside of the vertical member, these are where the shelves assemble into. As you can see, there's slightly different height square positions for each row of squares. And the difference between these two is the position of the OU and RU shelves. And the position of these dog ear tags prevents them from being put into the wrong location in the rack for integration. So here I've got some close-up images of the shelves mating at the point of where the clip locks into the vertical members to ensure it cannot be removed or fall out. So as you can see, when the dog ear tags are pushed into the squares initially before sliding back, the clip is raised on the front surface of the vertical member before full engagement when it's slid back. Once it's slid back into place, the spring clip can pop in past the vertical member edge and then prevent the shell from sliding back out unless the clip is released with a tool or by a trained person. So here is a cross-sectional image from the outside of the frame in of the vertical member looking through into where the spring clip engages over the front edge of that vertical member. And this is just to show how it engages and where people will have to release this clip to be able to remove these shelves if needed. So here is a aerial view of the ORV3 frame, and I just wanted to discuss the catch edge changes for between ORV3 and ORV2. So for ORV2 today, there are specific square cutouts along the frame vertical member for where the equipment latches pop into. For ORV3, there is no longer any individual squares for this process. We are just using the front edge flange of the vertical member to clip behind for the equipment. And this improves flexibility of location of the equipment throughout the frame. And Glenn will go into a little bit more detail as to where the clips have to be within the equipment for this.
Okay, we're going to go over the process to convert version 2 gear to version 3 gear. We're going to talk about in mechanical perspective, we're going to talk about V2 versus V3 basic features, the rear tab on the back of the chassis, adding a front vertical restraint feature, latch changes in terms of design and location, and replacing the 12-volt Medusa cable with a 48-volt Medusa cable. Then we'll touch briefly on the electrical part of it, where there's going to need to be a 48-volt to 12-volt DC to DC converter. So on the left here is a rear view of the V2 rack, and you'll notice there's some pushed out areas there. Those are called lances, and that is a stop for the IT gear to keep it from continuing to the back of the rack. And the little tab shown there goes into that lance and vertically constrains the chassis up and down. On the right, let me explain what we're looking at. The light blue is the actual representation of the IT gear, and the dark blue is the rack rail. So in terms of a front to back stop, the rail has a bent flange that you see there, and when the gear is installed, it stops on that, and that's what keeps the gear from going rearward. There's also a tab that's designed in that goes into a slot in the rail, and that's what vertically constrains the IT gear at the rear. This is a simplified representation of an IT gear for V3. So at the rear, there will be a unique power connector. And then we talked about the details of the tabs and restraints that are needed at the rear. So that was discussed on the previous slide. And on the right view there is a side view of the front of the chassis on the side of it, showing that light blue arched surface is a vertical restraint. What that does is it goes into slots designed into the rack rails, and that constrains the front of the chassis from going up and down. And then the lower arrows pointing towards the IT gear latch, which is going to be in a somewhat different location, slightly different location versus V2, and also will have a taller profile. On the left side there is a picture of a V2 gear showing the Medusa clip connectors, and on the right is showing the snap-in style Medusa clip, the 48-volt version for V3, and it's just showing you visually the differences between the two. This is a picture of the comparison between the 12-volt Medusa cable on the upper larger one there, that's from V2, and the 48-volt Medusa cable down below. Now the power differences are a little bit lower on the 48-volt, but you can see there's a very large difference in the amount of copper needed when you're going from 12-volt to 48-volt. This just was to show a visual comparison of the size differences. This is a picture of a V2 chassis with the cover removed, just showing from the bus bar clip to the inside of the chassis, that those areas will be different, and somewhere within the chassis electrically, you will need a 48 volt to 12 volt DC to DC converter. Now I'm going to get into the efforts we've kicked off with OpenRack V3 liquid cooling. We formed a focus group to develop liquid cooling blind mate interfaces, and that's been going on for a month or two now. We've developed, in that group, we're going to be developing specifications and solutions for the community. We're going to be developing manifold specifications for interfaces. We're going to be developing blind mate triplets quick connectors with a specification. We're also going to be working on the interfaces between the manifolds and the IT gear. That would include things like the actual design of the rear, where the quick connectors are going to install, where they should be, what that geometry looks like, as well as ejector concepts and tolerances to ensure that the valves will be open and performing correctly in their useful range. And then on the frame side, we're going to be developing the interfaces and features for the manifold. And Steve showed some preliminary pictures of some of the ideas that we're working on. So there will be details on the manifold as well as on the frame specifications, so that everything is well defined. We're also, one of the key things to come out of this, and one of the goals, is to have supplier interoperability. So we want it so that vendor A valves can work with vendor B valves. You can have a mixture on a system, and they will perform the same. So what are some of the challenges? Well, there's some large challenges when you're dealing with a big rack that's optimized for service, and you're dealing with also dealing with high mate forces and deflections because of the spring forces, as well as the water pressure that's required. The manufacturing tolerances on the manifolds is a big challenge as well, because these manifolds are fairly long, over 2 meters long, and trying to keep them within the appropriate form tolerances that are reasonable and still have the valves operate within their ranges is a challenge. And I jumped ahead a little bit, but service optimized. What that means is this rack is designed for ease of service, so that creates more challenges in terms of design gaps and tolerances. And so those are all the challenges that we're dealing with in terms of liquid cooling. And what does that, how do they show themselves up? Things like the working range of the quick connector valves needs to be longer than a traditional one. The ability to take up misalignment because of the blind mating of it, hence for the service optimized design, are all big challenges. So what's next? We're going to continue to work with the community on the rack features. We're going to define rack interfaces for the liquid cooling. We're going to share preliminary specifications with the community, and we're also going to work on developing some prototypes. So we encourage the community, to those listening and those watching, to get involved. There's links here to the OCP wiki page, and down below there's the Rack and Power wiki page link. And you can also, by going to that link down at the bottom, you can be added to the Rack and Power mailing list. So that you can stay informed on projects and progress. So I just want to say thank you for listening.
Yep, thank you, everyone.
Hello, so thanks for everyone that's been listening. I've seen there's been a couple questions during the presentation. One of the ones in the chat, which I briefly answered, was people have been asking whether they can remove the shelves from inside or outside of the rack. And as some of the videos in that presentation showed, these shelves can only be removed from inside of the rack. So this would not be possible from the outside at the moment. So is there
Hello, this is Glenn. Sorry, Stephen. This is Glenn Stress. Hey, thanks for joining, everybody. Stefan, you had a question about the 48 volt to 12 volt converter. The rack actually does not have a converter within it, right? It has a bus bar. So what we were talking about is the infrastructure with the power shelves and eventually the battery backup work that's being done, along with a redesign of the rack with a new bus bar layout and design. we're going to be supporting 48 volts. So there's not actually electronics within the rack that has a 12 volt to 48 volt conversion. So hopefully that answered your question.
I see another question in the list there for the rack rail installation is toolless. Can you clarify if the removal of these rails is also toolless or not? So yes, the rails are designed so you can delatch them with your hand and remove the shell. So yeah, toolless.
Yeah, I see a question from Keith. Yes, the 3D CAD, we released a partial rack cross section that has the bus bar, some OU rack rails, and the rack frame in it via the OCP wiki, as well as via the Rack and Power email alias. So you can check that out at the end of the presentation. There's some links on there. You can go in there, and there's a section in there where there's a table of under development programs in the Rack and Power section. And there's a link there to a zip file that has a 3D step file that you can download. In terms of the OU and RU weight rating, I see that one's from Sebastian. Yes, they will have the same weight rating.
I think that's all the questions there, isn't it, Dan?
Yes, I think I clarified with Sebastian about the converter part of it. This is mainly a frame focus. So Stefan, and Sebastian and Stefan both asked the question. If you go on the Rack and Power wiki, you can take a look at some of the groups that are being organized around power, and you'd be welcome to look into that and maybe see if you can join and get more information if you'd like. There's a bunch of work going on in that area right now with a bunch of partners.
Okay, so if there's no more questions, thanks for everyone that's listened today. I hope it was informative, and we look forward to the next time we get to present to you guys.
Yes, thank you for joining. Be safe.